Hello everybody, I am Lup. I am an IoT educator from sunny Singapore. I used to teach IoT at a local school for evening adult education. Nowadays, I write educational articles about NuttX and publish them online. So my work in IoT education has kind of moved online. IoT gadgets today are becoming more sophisticated. Some of them have a touchscreen display, which explains why I'm so excited about today's presentation. Today I shall talk about LVGL Touchscreen Apps in NuttX and why it might be a good idea to build them in Zig. Typically, we build our touchscreen apps with LVGL. LVGL looks intimidating to NuttX developers, but it doesn't have to be that way. In a while, we shall see that it is possible to make LVGL friendlier and safer when we write LVGL programs in Zig. Zig is a newer programming language that works well with C, and it looks suitable for creating LVGL touchscreen apps. We shall talk about wrapping the LVGL API with Zig and how it helps our developers. Since we are testing LVGL on a RISC-V device, like this Pioneer Stack BL604, I shall explain the challenges of running NuttX on RISC-V. If you'd like to download the presentation slides, please head over to this link, lupyuen.github.io/NuttX. Dex, the letter L, not the digit 1. All my presentations, articles, and source code are available at that link. We shall test our LVGL app on this device, Pioneer Stack BL604 with ST7789 LCD display and Buffalo Lab BL604 SoC inside. We're looking at the touch panel calibration of our touchscreen app. Pioneer Stack has an I2C touch panel. We can see that the touch panel responds correctly in our LVGL app. Let us talk about LVGL. LVGL is a very popular graphical user interface library for microcontrollers. It works great for rendering text, graphics, buttons, and other interactive widgets. In fact, I first used LVGL on a PineTime smartwatch, then I ran it on PinePhone. LVGL is natively supported by NuttX. It works great with NuttX frame buffers, LCD devices, even touch input devices. There is a demo app bundled with NuttX, but be careful. The code is super verbose because it tries to create all kinds of LVGL widgets. For today, we shall look at a simple LVGL demo that creates a single text label. Here is our super simple LVGL app. It doesn't do much, but the code is actually quite lengthy. Before we create our label, we need to fetch the active screen. This is how we do it. Then we create our label, passing the active screen as the parent widget. Now we set some properties on the label. Our label should wrap the text if it's too long, and our label will have embedded colors. So it will show the text in multiple colors. But wait, we're not done yet. We align the text to the center of the label, and we are ready to set the text or label now. This prints 3 words, hello, Pioneer, and stack, in red, green, and blue. That's because we inserted the color codes into the text. We set the width of the label in pixels. Finally, we align the label to the center of the screen. Let us flip back to the earlier code. Imagine a person writing LVGL code for the very first time. LVGL looks super intimidating, doesn't it? So much repetition, right? LV everywhere, super long function names. What about safety? Can we be sure that these 2 functions won't return a null pointer? I would probably add assertion checks to be sure. So can we make LVGL coding simpler and safer? Maybe with the Zig programming language? So here is our proposition for today. Let us tweak the LVGL code so that it looks simpler and safer, with a little help from Zig, the newish programming language. Zig is so new that it hasn't quite reached version 1.0 yet. There are some limitations I shall explain in a while. Zig works well with C, so importing LVGL types and functions into Zig is a piece of cake. Zig will check for null pointers and other runtime problems that we commonly miss, so our LVGL app will actually become safer. Zig can infer missing types from our code, so there's less repetition and clutter in our code, easier to focus. Zig will even automatically convert a program from C to Zig. The converted code looks long and verbose though, but it's a good reference for studying the nuances between C and Zig. So you might be thinking, hey, I'm not familiar with Zig. You know what? I'm new to Zig too. We'll explain all the Zig features in this presentation. Let us take a peek at our Zig code. We no longer specify the LVGL types, like for screen and label. Zig infers the LVGL types for us, so our code looks less cluttered now. Notice that we use try when calling the LVGL functions. This is how we handle errors in Zig. If any of these functions return an error, the execution stops and the error is returned to the caller. This is why we specify the return type with a bang, exclamation mark or exclamation point. This means that this function might return an error. Nice tidy way to handle errors. The rest of the code looks similar to C, except that we move label to the front so that it appears more object-like. We shall explain later how we did that. The ++ here is for string concatenation, but it works only for constant strings at compile time, so it is safe. When we compare the C and the Zig versions of our LVGL app, the Zig version looks simpler, less repetition, less clutter. Yet Zig is actually doing more behind the scenes, like watching out for null pointers, underflow, overflow, array out of bounds. If something goes wrong at runtime, Zig will halt our program with a panic message and show a helpful stack trace. Let us go deeper into Zig and understand how exactly it makes our program simpler and safer. First, we talk about C macros and declarations. To import them from C to Zig, we write a C import like this. For C macros, we change hex define to at C define. So hex define NuttX becomes at C define NuttX. How did we get these defines? We'll come back to this. For C declarations, we change hex include to at C include, which we shall see in a while. How is it possible that Zig can understand C macros and declarations? That is because Zig calls the CLang compiler to pass C macros and declarations, which makes it really easy to import C functions into Zig. Remember we talked about changing hex include to C include? This is how we do it. With this couple of lines of code, we have imported all the C header files that we need for NuttX, LVGL, and our app. The first two lines look out of place, types.h and limits.h. I ran into some macro problems without these lines, so I added them. Could be a problem with CLang. That's all for importing C functions into Zig. No wrappers needed. This is how we call the functions imported into Zig. If we compare the Zig code at right with the original C code at left, they look highly similar because we haven't read the LVGL functions yet. We'll talk more about this in a while. Do you see the dot question mark at the end of the line? Zig will verify that the result is not null. If these functions return a null pointer, Zig will stop our program with a panic message and show a helpful stack trace. To compile our Zig code for the RISC-V BL604 SoC, we run this command. Then we link the object file with NuttX. How did we get these compiler options? We copied them from NuttX, as observed with make trace. This is what we observe with NuttX and make trace. Here are the options that we copied from GCC to the Zig compiler. Now, what about the rest of the GCC options, like NuttX, NDebug, RISC-V? Well, we copied these C macros to our Zig program as C defines, since the Zig compiler won't accept these options. Earlier we saw this Zig target and CPU when compiling our app for BL604. What is baseline RV-D? Well, BL604 is officially designated in RISC-V as RV32 IMAC-F, which means that BL604 has all these goodies, IMAC-F, including hardware floating point, single precision. Now this is almost similar to baseline RV32, which is RV32 IMAC-FD. The D here means double precision floating point. Now, since we don't have double precision floating point, we subtract the D, right? Remove it, but keep the single precision floating point. That's why baseline RV32 minus D is equivalent to RV32 IMAC-F. Things get a little quirky for Zig on RISC-V BL602, since Zig hasn't officially reached version 1.0 yet. The binary produced by Zig compiler says that it's using software floating point ABI for application binary interface. But we told Zig compiler to use hardware floating point. The binary produced by Zig won't link with NuttX because the rest of the binaries are hardware floating point. This is a terrible hack that modifies the ELF header from soft float to hard float. Our Zig binary will link successfully with NuttX after this hack. We tested the Zig app on Pioneer Stack BL604 by Pine64. This gadget is based on the BL602 RISC-V SoC by Buffalo Lab. Check out my presentation on NuttX on a RISC-V IoT gadget, Pioneer Stack BL604. The app begins with touch panel calibration, which still runs in C because we haven't finished the conversion to Zig. Then it calls our Zig code to render the line like this. We see the text label with the color text in red, green, and blue. So yeah, our LVGL app runs correctly on Pioneer Stack BL604. This is a demo of our LVGL Touchscreen app in Zig running on Pioneer Stack BL604, which has an onboard ST7789 LCD display and an I2C touch panel. We have compiled the Zig touchscreen app into the NuttX firmware. Pioneer Stack is now booting the NuttX firmware. The screen turns pink when NuttX boots. Uname says that this is a recent build. NuttX version 10.4.0. Let us check the NuttX devices. We see the LCD device, LCD0, that is connected to the ST7789 LCD display. Our touchscreen app will render graphics to that LCD device. And we see the touch input device, input 0, that is connected to the CST816S touch panel. Our touchscreen app will read touch input from that device. Let us run the touchscreen app. Remember, this is a Zig app that we have compiled and linked into NuttX, though it still contains some C code. The touchscreen app begins with the touch panel calibration. We need to tap all four corners of the screen to complete the calibration. This is coded in C because we haven't converted the calibration code to Zig yet. The screen refresh looks laggy. Hopefully this will be fixed when SPI DMA has been implemented for BL604. When we tap the screen, the touch input driver captures the touch coordinates and passes them to our app. After computing the calibration, our app renders a simple text label, Hello, Pineo, Stack. Remember the Zig code we saw earlier? This is the output from our Zig code. And that was a demo of our LVGL touchscreen app in Zig on Pineo Stack BL604. Let us head back to our Zig code. When we last saw our Zig code, we were calling the LVGL API that we have imported from C, which looks long and cumbersome like this. Can we wrap the LVGL API with Zig and make it object-based so that it looks more friendly? This is what we mean. We move the LVGL widget to the front, right? Like these. And we shorten the function names from this to this. So the code looks more sensible. We do this by wrapping the LVGL API with Zig. Inside our LVGL wrapper, we call the LVGL API, like getting the active screen. When the LVGL returns the active screen, we wrap it inside a Zig object, like this. This Zig object will be used by our LVGL app to perform LVGL operations. We need to do this wrapping for every kind of LVGL widget, buttons, labels, text areas, and so on. It will be tedious, but hopefully worth the effort. By the way, this funny notation with the screen and bar S bar, this means that if screen is not null, then S becomes the value of screen. But if screen is null, then we do the else clause. Remember that we use the active screen to create a text label. We need to wrap this as well. Inside our wrapper, we call LVGL to create a label. And we return it wrapped as a Zig label. Our label allows setting of text and properties. This is how we define the functions for our Zig label. These functions will forward the calls to the LVGL API, right? It looks highly mechanical. Maybe we can automate this so we don't need to write out every single wrapper by hand. We shall come back to this. After wrapping our LVGL API with Zig, we get this neater, tidier version of our LVGL app that we saw at the start of our presentation. This code runs okay and renders the label correctly. But if we try to do anything else in LVGL, our wrapper might not support it because our wrapper is incomplete. To build a complete LVGL wrapper, we might need some automation Zig compiler can generate a type info JSON that describes all the types and functions imported from LVGL. We could scan through the type info JSON and auto-generate the LVGL wrapper. However, we might have a problem designing the LVGL wrapper because LVGL is actually object-oriented. It supports widget inheritance. Zig isn't an object-oriented language, so mapping LVGL widgets to Zig can get challenging. Now that we have a simpler, friendlier way for our LVGL developer to build touchscreen apps, let's talk about safety. Zig performs safety checks at runtime. If we try to dereference a null pointer, or if our computation causes an underflow or overflow, if we try to access an array beyond its bounds, all these will trigger a Zig panic, followed by a helpful stack trace, which is really helpful for tracking down the bug. Zig isn't memory safe yet. It doesn't have a borrow checker for compile time checking, so Zig might have problems tracking our heap memory. Problems like use after free. See this article for the details. Some of us might wonder, if Zig is really so great, why isn't everyone using it yet? Well, Zig is still new. It hasn't reached version 1.0 yet. Some things are a little rough. This is one of the quirks that we have to live with for now. LVGL defines this struct that represents color. This is RGB 565 format. 5 bits for blue, 6 bits for green, 5 bits for red, total 16 bits. Notice that it's implemented with bit fields. Sadly, this is a no-no for Zig. Zig will refuse to import struct types with bit fields. Instead, it becomes an opaque type in Zig. We can pass pointers to it, but we can't create instances of it, and we can't access the fields inside. The workaround is to access the bit fields in C, and Zig will have to pass the struct pointers to C. This complicates some widgets in LVGL, like the canvas widget, which uses color type. Since we're running NuttX on RISC-V, let me share some thoughts on the RISC-V ecosystem and how it affects NuttX. Sadly, the RISC-V ecosystem today is severely fragmented. RISC-V microcontrollers like BL602, ESP32, GD32V, FE310 all have vastly different internals. Memory layout is completely different. How we handle interrupts is also different. It's not easy to jump from one platform to another. Now, Buffalo Lab has two families of RISC-V SoCs, BL602 that we've seen earlier, and BL702, like this photo that we see here. Yet, BL702 is so different from BL602 that NuttX won't run on BL702, right? So it gets rather frustrating. I understand that we might be creating a unified makefile for NuttX that will support C, Zig, and Rust. Now this might be challenging for RISC-V. We've seen earlier that RISC-V needs a special target for Zig, but for Rust, we actually need to provide a custom target JSON that will support hardware floating point on RISC-V, like for BL602. There's one last thing that makes BL602 frustratingly different from other microcontrollers, and it causes problems with a touch input for our LVGL app. You know, when we talk to I2C devices on I2C bus, we need to send the register ID inside the I2C request. Well, BL602 calls this the I2C subaddress, and it mandates that we send the I2C subaddress through a dedicated hardware register. But NuttX assumes that I2C subaddress is part of the I2C data. So right now, NuttX extracts the I2C subaddress from the I2C data. Under some conditions, it doesn't quite work correctly. Perhaps we might need to extend the NuttX I2C interface to support I2C subaddress as a separate parameter. Since Zig has proven to work so well on NuttX, we plan to do more experiments with Zig on NuttX. We are now porting NuttX to PinePhone, this mobile phone based on Allwinner A64 SoC. Why port NuttX to PinePhone? Well, I think it's highly educational to document the process of running NuttX on a real phone, something that we might use every single day. Someday, we might even use PinePhone to teach our students about the internals of NuttX. The progress has been great. NuttX now boots OK on PinePhone, all the way to the NSH shell, as we see in the photo here. We have plenty of NuttX drivers and apps to build for PinePhone. We need a quick and safe way to prototype these drivers and apps on PinePhone. Zig might be super interesting for doing this. Check out the progress here. If you are keen to learn Zig, here are some helpful links. Zig Learn is probably the best tutorial for Zig. The Zig language reference is a readable, concise guide for the entire Zig language, which isn't really that big. Many of the Zig features are implemented in the Zig standard library, so we should refer to the official documentation. Zig News has plenty of insightful articles. The Zig community on Reddit has friendly folks who might be able to help if we have a question about Zig. If we need more information about compiling Zig apps and Zig method programming, check out these guides. Also check out my presentations. The first presentation is on Zig programming for NuttX sensors. We explain the compile time features in Zig and how we use them to read NuttX sensors. The second presentation is about PioneerStack BL604, the new RISC-V IoT gadget, and how we plan to build Zig apps for the device. I've been using Zig for the past 5 months. Before that, I've been using Rust for a couple of years. To wrap up today's presentation, I would like to share my thoughts on Zig. Zig works surprisingly well with NuttX. Zig can call NuttX functions without any bindings or wrappers. Well, unless we intend to redesign the API, which we did for LVGL today. Zig lets us import NuttX types and functions directly into our Zig programs. This is a big plus. I just hope that Zig will release version 1.0 soon, so that Zig will support structs with bit views. Zig's safety checks at runtime are helpful. They save me the hassle of writing assertion checks everywhere in my C code. The runtime safety checks will be especially helpful for people coding NuttX apps for the very first time. The safety checks are good for education. If I ever need to teach programming in school, I will definitely teach Zig. Unlike C, Zig doesn't have macros, but Zig allows us to write code that will be executed at compile time, and it works as well as C macros. Check out the details in my presentation of visual programming with NuttX sensors. In this presentation, we have covered many topics. Everything that I've covered is explained in these articles. Our touchscreen app in Zig, how Zig runs on RISC-V BL602, and PioneerStack BL604. If you would like to download the presentation slides, please head over to this link, lupyuen.github.io/NuttX. That's the letter L, not the digit 1. All my presentations, articles, and source code are available at the link. The first article from the previous slide has plenty more details on LVGL and Zig that we have omitted from this presentation, like how we worked around Zig's inability to import structs with bit fields, and how we ran the Zig compiler to auto-translate an LVGL app from C to Zig. The fixes that we made to handle opaque types in the LVGL input driver and color type, plus a walkthrough of the type info JSON generated by the Zig compiler and how you might use it to create the LVGL wrapper in Zig. The details are all inside. Please check out the article. LVGL looks a little less intimidating to NuttX developers now that we have Zig. Zig is now supported on NuttX, and it's a wonderful thing because Zig will helpfully do all kinds of safety checks at runtime. I hope NuttX developers will find it a lot more productive to code in Zig. Since we are now porting NuttX to PinePhone, let us create more drivers and apps in Zig. Thank you.